Hello and welcome to my next video on transition metals. A transition metal is a d block element that forms an ion with an incomplete d subshell. So the d block in a periodic table is the bit between group 2 and group 3. So the ones that contain elements from left to right on the top row, scandium to zinc. So we'll look at zinc and why it isn't a transition metal. But it has to form at least one ion. It can form more than one, but it has to form at least one where the d subshell is incomplete. A d subshell holds 10 electrons, so one ion has to have at least 9 or less. So here are some electron configurations. Now a few things to remember. When writing electron configurations, 4s comes before 3d, and when you take away electrons, the 4s is emptied first before the 3d. So you'll see here, iron has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. But the ion Fe2+ is 1s2, 2s2, 2p6, 3s2, 3p6. Then the 2 electrons, because it's 2+, it means it's lost 2 electrons, have been lost from the 4s subshell, meaning it's got no electrons in its 4s, and then it's just 3d6. 6 is not 10, so it is an incomplete d subshell, so it is a transition metal. Now there are 2 exceptions you need to know. That's copper and chromium, and they're why they are exceptions because they fill up only 1 electron in the 4s subshell. And they say this might be due to they have the most stable configurations because the electron repulsions between the outer electrons are minimized. And they say this because in copper, the 3d subshell is completely full, and in chromium, the 4s and 3d are both exactly half filled. So each orbital, which contains 2 electrons, has 1 in it. But anyway, here copper, you can see 1s2, 2s2, 2p6, 3s2, 3p6, 4s, 1, 3d10. Now let's say I see you copper 2+ ion, 1s2, 2s2, 2p6, 3s2, 3p6, loses 1 electron from the 4s first, and then another from 3d, meaning it's got 3d9, 9 isn't 10, so it's got an incomplete d subshell in one of its ions, so it's a transition metal. And now to see why zinc isn't. Zinc is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Now zinc can only form a 2+ ion. So we have, well, it can form 1+, but we say it forms up to a maximum of 2+. So then 2+ is 1s2, 2s2, 2p6, 3s2, 3p6, loses 2 electrons from 4s2 first. So it's got no 4s electrons, leaving just 3d10. That's a full d subshell, so zinc is not a transition metal. Now this is AS stuff, knowing how to write the configuration, so I hope you do know that. Properties. Now properties of transition metals, firstly they've got similar ones to all metals, so they are shiny, they have a high density, high melting and boiling point, they can form giant metallic lattices. Now other things, they have variable oxidation states. Now if you remember oxidation numbers from AS Unit 1, you should remember what they are. But it's example here, vanadium can form a V ion, a V+, V2+, V3+, V4+, and V5+. And I've given 2 examples of compounds vanadium forms. We have VO2+, well, VO2+, and VO2+. You can see the difference. Now in VO2+, we have an overall charge of 1. Oxygen always has an oxidation number of -2. So something -2, because there are 2 oxygens, equals 1. Well, that is 5. 5 -2 -2 equals 1. So here, vanadium has an oxidation state of 5. In VO2+, it is something -2 equals 2. Well, that's 4. 4 -2 equals 2. So vanadium has an oxidation state of 4. So here, variable oxidation states. And some other good examples you need to know about is potassium manganate, which is KMnO4, and potassium dichromate, which is K2Cr2O7. And what they have is they have these compounds in their maximum oxidation state. So manganese can go up to +7 and chromium can go up to +6, and they are found in these two compounds. So it's a good two to look at, the potassium permanganate and the potassium dichromate. And also all these molecules form coloured compounds, and they all have a very specific compound, because when white light passes through their solution, some of the wavelengths of visible light are absorbed and some aren't. Now the colour that we see is the light that isn't absorbed. So copper 2 sulfate appears blue because all light is being absorbed apart from the blue light. Colour is formed by partially filled d orbitals in transition metal ions. So if the ion has no electrons in the d subshell at all, it's not going to produce a colour. So you can have colourless ions as well. Now they can also act as catalysts. So there are some examples in the book, but catalyst in the Haber process you use iron. In the contact process you use vanadium oxide. In the hydration of alkenes use nickel. In the decomposition of hydrogen peroxide use a suitable catalyst is manganese oxide, but you can also use potassium iodide. But yeah, they can act as catalysts. Learn all of these. So I've seen horrible questions where they will literally list about 5 properties and ask you to name another 3. Reactions. Now, I'm going to go through 2 of the main reactions that transition metals can do. There are 4 ones. There's acid-base, redox, precipitation, and Ligand substitution. Redox reactions and acid-base reactions have been covered in different videos, so I'm not going to go through them on this one, but I will go through precipitation and Ligand substitution. Now, a precipitation reaction is when you just have 2 solutions are mixed to produce an insoluble compound, and that insoluble compound suspended in a liquid is a precipitate. Yeah. So here are some examples. Now these are the ionic equations. Now to make a precipitation reaction we add sodium hydroxide because we want the hydroxide ions. So you could do copper sulfate plus sodium hydroxide becomes copper hydroxide plus sodium sulfate. But in this case we have just the ionic equation with state symbols. Cu2 plus aqueous plus 2OH minus aqueous becomes copper hydroxide solid. And all you just have to remember is how whatever the charge on the transition metal ion is, that's how many molecules of OH minus. So Fe3 plus has 3OH minus becoming FeOH3, which is a solid. And you need to know the colours. Now, copper solution is pale blue and it forms a pale blue precipitate. Cobalt 2 plus is a pink solution which forms a blue precipitate, and then when it's expressed and not expressed in the presence of air, it produces a beige colour. Iron 2 plus is a pale green solution, forms a green precipitate, and when in air it oxidizes to form iron 3 plus, so you get a rusty brown or a brick red colour. Fe3 plus is a pale yellow solution, which then turns rusty brown or brick red when it forms its precipitate. Now, complex ions. A complex ion is a transition metal ion bonded to one or more ligands by coordinate bonds. So we now need to explain those 2 terms there. Ligands. A ligand is a molecule or ion that can donate a pair of electrons with the transition metal ion to form a coordinate bond. So, water, H2O. The oxygen has a lone pair, it can donate it. Other examples, NH3, ammonia, can donate electrons because it's got a lone pair. Thiocyanate, SCN minus, can donate electron pair. Cyanide can donate an electron pair. Chloride and hydroxide, you can see. Now, a coordinate bond is a bond in which one of the bonded atoms provides both electrons for the shared pair. Basically, it's a dative covalent bond. And the coordination number is the total number of coordinate bonds formed. Now, I've given an example here of hexa aqua copper, I believe is the name. Does it say anywhere? Okay, I believe it's hexa aqua copper. You don't need to know how to name them, so don't worry. Here, you have the copper ion centrally, surrounded by water. Now, 6 water molecules can donate their lone pair of electrons to copper, and you get this 3D shape. You get two molecules which are up and down in the plane, and you've got two which come out towards you and two which go away from you, which means that all of them have a bond angle of 90 degrees. And as you can see by my badly drawn angles, I've drawn one 90-degree angle, but the rest I've drawn as kind of L shapes. That shows 90 degrees. All of them are 90 degrees basically. And this produces an octahedral shape, octahedral because there are 8 faces. And I've said Cn, which is a bit confusing because I said cyanide earlier. Cn for coordination number is 6 because there are 6 bonds. Now the ion is Cu2+. Water has no charge, so the overall charge of the complex ion, which you put in brackets, is 2+. If all of these were hydroxide ions, 1-, they count to the charge. You have Cu2+ with 6OH- becomes 4- overall. And we write this when we're writing in equations. You do square bracket Cu bracket H2O close bracket 6 close big bracket 2+. And we call the ligands we're using here that can form one coordinate bond as monodentate ligands. And we'll look next at bidentate and multidentate. Bidentate means that the ligand can produce 2 coordinate bonds. Multidentate means it can produce however many. Now 2 molecules you need to know as bidentate ions. You need to know En, which we call it En, is actually ethane 1,2-diamine, and that's the NH2CH2CH2NH2. You need to know that. And you need to know ethane dioate, and that is the COO minus COO minus. So it's basically like a dicarboxylic acid but without the H's. So remember, there's a negative charge on them, so they will affect the charge of the complex. So here I've done Cu2+, and as you can see, the one molecule, I've done it in skeletal form because you don't need to draw the carbons skeletal. You can see that each molecule forms 2 bonds, and there are 3 molecules around it, and it produces a 4- charge. It's basically the same as monodentate, but there are just two bonds for each molecule. And multidentate, you need to know of EDTA 4-. I haven't drawn it because it's quite hard to draw, but you can see. So it's got in the centre, it's got N CH2 N, and each N is connected to 2 CH2 COO minuses, and so the N can donate a pair of electrons, and each of the oxygens can. So you have 6 possible bonds being able to form. So it will be able to bond just with that one molecule completely to another molecule, or to a transition metal ion. And it's important to say the coordination number is the number of bonds formed. So in the bidentate, 3 molecules each have 2 bonds, so it's still 6. There are still 6 bonds, but they're just contributed from 3 molecules. Now, stereoisomerism, you can have EZ isomers. Now here I've firstly shown you another type of shape you can get. Now you can get a square planar shape, and this is where you have a molecule which has a coordinate number of 4. So they're arranged at the corners of a square, and it's like an octahedral shape but without the ligands above and below. So it's just basically a flat plane. And here we have copper, 2 Cls and 2 NH3s. And it's just the same cis and trans. So cis, we have the ligands on the same side. On trans, we have them in opposite sides. This means in the cis one, the chlorines are 90-degree angles apart. And in the trans one, they're 180 degrees apart. So you can also have it in a molecule with 6 ligands, and again it's the same. Just make sure when you do cis and trans, cis the molecules are 90 degrees apart, and in trans they're 180. You also have optical isomerism, and this forms when you have a complex, an octahedral complex that contains multidentate or bidentate ions. And you just do it like you do normal optical. Draw the molecule. So you can see, as I've drawn in the bottom, the shape is like a Y, but remember, since it's actually got 90-degree bond angles, it isn't quite a Y, but it's like a Y if you look at it. And then the opposite is the reverse Y. So just, one's a sideways Y, one's the reverse sideways Y. I mean, to be honest, I can't really explain it much more than you just look at it and see how it's drawn. So basically you just draw them, and then mirror it. That's how you do optical isomers. Now, ligand substitution, the other sort of reaction. Ligand substitution is a reaction in which one ligand in a complex ion is replaced or substituted by another ligand, so it makes sense. Now, in the first example, we've got hexaquicopper, Cu with 6 H2Os plus 4 NH3s, and that will, the 4 NH3s will substitute with 4 H2O, so you get Cu, NH3, 4, H2O, 2, 2 plus 4 H2O. It's pretty simple. Now, what will actually happen is when you add ammonia, you will actually get a pale blue precipitate forming first. But when you add more ammonia, excess ammonia, the precipitate dissolves and you actually get a deep blue solution. Now, in this complex ion, if you have two different sorts of ligands, each one will have different bond lengths, so you get kind of distorted shape. You don't get a pure octahedral shape, you get a distorted octahedral shape. Now, another example is with copper again, but if you add 4Cl-, you can do the Cl in brackets in the new complex as Cu bracket Cl4. You don't have to. I sometimes have and sometimes haven't. Your choice. You won't lose marks doing it or not doing it. But the 4Cl will substitute all 6 H2O because Cl, a chlorine molecule, is bigger than a water molecule, and so these chlorines have stronger repulsion. So fewer chloride ions or ligands can fit around the central transition metal ion. And with these ligand substitutions, you get, as you can see, equilibrium occurring. So yeah, so they can also go in equilibrium reactions. Now you need to know a few examples. You need to know the hexaquicopper complex is pale blue. When you substitute NH3 in, so you get Cu H2O2 NH3 4, you get a dark blue solute colour. Copper with 4 chlorines is yellow. Cobalt with 6 water is pink, and cobalt with 4 chlorines is blue. And that's what you need to know. Now there's an example of ligand substitution which happens in the body which you need to know about. Now naturally, hemoglobin will contain Fe2+, a transition metal ion, which can form 6 coordinate bonds. Well, it has 1, 2 globin, because we have heme, which is the heme group, and you have globin. You have 4 coordinate bonds with nitrogen, so you have 1 which can then pick up oxygen. But that's what hemoglobin's role is. It's found in red blood cells and it's to pick up oxygen. Now, it will pick up oxygen at the lungs, take it to the cells, and oxygen will be given off and carbon dioxide will be taken in its place. And it's kind of the carbon dioxide and the oxygen have a ligand substitution reaction. But the important thing is carbon monoxide. Carbon monoxide can go into a ligand substitution with oxygen, but the dangerous thing is that it is permanent. So if you get carbon monoxide, which is more likely to bind with hemoglobin than oxygen, once carbon monoxide is bonded, it will stay there permanently until the cell dies, which I believe is about 40 days. So after about 40 days, your cell will die and you'll get a new one. But for those 40 days, that red blood cell is useless if the hemoglobin is bound to carbon monoxide. Now, you don't need to know this in a huge amount of detail, but just basically know hemoglobin contains Fe2+, which can form a complex ion, and it can go through ligand substitution of oxygen with carbon monoxide. When carbon monoxide bonds, it is permanent and will not be substituted. And finally, the stability constant. Now, this is very simple. I'm not going to go through it too much because the stability constant is exactly the same as the equilibrium constant, Kc, but except you don't have water. So if you want to look at more how to do these, look at the equilibrium constant video. So equilibrium. But what happens is, if you have the reaction, let's say hexacobalt plus 4Cl- becomes cobalt chloride plus 6H2O, the stability constant is, now remember it is product over reactant, so the concentration of COCl4 over the concentration of COH2O6 and the concentration of Cl minus to the power of 4, because there's a 4 in front of the Cl minus. But on the top, a product is water, but you don't put it on the top, you just ignore water. And the reason you do this is because all species are dissolved in water, which is in large excess, and its concentration is virtually constant, so there's not much point. So basically, for this slide, watch my equilibrium video, learn the equilibrium constant, and then when you're doing K-stab, just leave out the concentration of water, ignore it. And that's all. Thank you for watching. So in conclusion, you have transition metals, which are metals which form at least one ion with an incomplete d subshell. And you have to know the electron configurations and properties of transition metals. You need to know the 4 reactions: ligand, substitution, precipitation, redox, and acid-base. Redox has been covered in the cells, the chemical cells video, and acid-base covered in acids. They can form complex ions, which are with ligands, and you need to know the stability constant. So I hope that all makes sense. As usual, like, comment, if you liked the video, if it helped. If you didn't like the video, feel free to dislike, but please tell me what you disliked about it so I can improve and help you. If there's anything you didn't understand, leave a comment or email me. And thank you for watching, and goodbye.